When astronomers of the early 20th century peered through their telescopes, they saw objects that no one had ever seen before. In the 1920s, the existence of other galaxies outside of our own Milky Way was revealed, vastly augmenting their knowledge of the universe. At this time, astronomers thought that everything in the observable universe was made up of the same stuff that we find here on Earth. That is, the universe was made up of atoms, with protons, neutrons, and electrons. Today, we now believe that conventional matter makes up only a very small portion of the universe. In fact, astronomers estimate that observable objects like planets, stars, galaxies, and clusters make up only about 4% of the entire universe. What then is the rest of the universe made up of? Astronomers now know that a very sizable chunk of the universe is made up of dark matter. But what exactly is dark matter, and how do we know it's there? Furthermore, how do we know that galaxies like ours contain lots of it? The answer to the first question is simple enough. We don't know what dark matter is made of. But we do know that it exists, and we do know where it exists. The discovery of dark matter can be traced back to the 1930s, when a California Institute of Technology professor by the name of Fritz Zwicky was observing the Coma Galaxy Cluster. Zwicky noticed that the galaxies in the cluster were moving much too fast for their own good. According to his calculations, the masses of the galaxies he could see were much too small for them to remain stable at the speeds that they were going. In fact, they would need to be at least 100 times more massive than he observed them to be to remain bound together by the force of gravity. He concluded that there must be some unseen mass acting gravitationally on the galaxies, keeping them from flying out of the cluster. He called this invisible mass dark matter. What we know about dark matter is that it has an attractive gravitational force, much like every other massive object in the universe. We also know that it neither emits light nor interacts with light in any way, hence why it is invisible to any telescope we possess today. But still, dark matter's true identity remains unknown. So, we know that dark matter exists in galaxy clusters, like the one that Fritz Zwicky observed, but does dark matter exist elsewhere in the universe? And if so, where exactly is it located? Is it found everywhere in the universe, spread uniformly across its entirety? We know that dark matter definitely exists in places other than the cluster that Zwicky studied. In fact, we know that dark matter exists everywhere where there's an observable, massive object. It even exists in our own galaxy. How do we know? The evidence comes not from observations made of the Milky Way, but of our neighbor galaxy, Andromeda, a spiral galaxy which is believed to be very similar to ours. In the 1980s, an astronomer named Vera Rubin was observing the rotational speed of the Andromeda galaxy when she noticed something peculiar. According to Newtonian physics, which still holds mostly true to this day, an object's orbital speed depends upon how far away it is from the body it is orbiting. The closer an object's orbit is to the body it is orbiting, the faster it goes along in its orbit. In the same way, the farther an object's orbit is from what it's orbiting, the slower it will orbit. This is exactly how our own solar system works. The orbit of, say, Jupiter is much slower than the orbit of planets closer to the Sun, like Venus or Mercury. Using this knowledge of physics, Rubin expected to find that the ends of the spiral arms of the galaxy rotated around its center more slowly than the parts closer to the galactic core. Imagine her surprise when she discovered that the orbital velocity of the stars and gases in the galaxy remained constant as she measured farther and farther away from the center of the galaxy. In other words, everything in the Andromeda galaxy was moving at the same speed, regardless of how far away it was from the central object exerting a gravitational force on it. Rubin was faced with a similar conundrum that Zwicky faced 50 years before. There was just not enough visible mass to justify the speeds at which these orbiting bodies were traveling. At the speeds she measured, the Andromeda galaxy should have been flying apart instead of remaining stable, just like the Coma galaxy should have been when it was observed by Zwicky. In order for the Andromeda galaxy to remain stable, there simply must be more mass than what is observable by telescope. In essence, a sort of halo of dark matter must be surrounding the galaxy, giving it mass and stability. Rubin's observations, and many others made of other galaxies since then, are the reasons that we know dark matter exists in our own Milky Way galaxy. We can only infer that if all of the other galaxies exhibit this behavior, so must ours. It is nearly impossible to measure the orbital velocities of the spiral arms of our galaxy, simply because there is so much dust and other debris blocking our view from Earth. We are forced to make judgments about our galaxy based on the observations of others like it, and we can only hope that the Milky Way is not a special exception in the vastness of the universe.